In this video, we will talk about measures of association. There are two measures of association. One is called the covariance, and the other one is called the correlation. Now, the covariance is nothing but represented by s of x, y. X and y are the two variables for which we would like to find the association. And so, to figure out the association between x and y, we take each value of x and see how far they are from the mean, and then you do the same thing for the other variable. See how far is each value of y away from its mean, and take the product of the two, because you would like to see the association between the two variables. So and then you would add across all the observations and then divide by n minus 1, uh, basically for adjusting for degrees of freedom. Correlation, which comes out of covariance, we will represent it by this letter R. So the correlation between x and y is nothing but the covariance between the two variables divided by the product of the individual standard deviation, right? Obviously, by logic, one can clearly see that the correlation between any two variables will always be between +1 and -1. So the idea of +1 is that it's perfectly positively correlated, and the idea of -1 being it's perfectly negatively correlated, and everything in between. You could have a zero correlation, basically saying there is no correlation. So let's take an example to understand how does one go about calculating this correlation and covariance. So let's assume you have two variables, xi and yi, right? And xi takes the value 5, 10, and 15. This is just for simplicity. And yi takes the value 10, 30, and 50. Now notice, to figure out correlation and covariance, one has to see how far is each x from its mean, so xi minus x bar, and how far is each y from its mean, so yi minus y bar. And then we also need the standard deviation of x and standard deviation of y, for which you would need to look at the squared deviation as well. So you have xi minus x bar squared, and then you have yi minus y bar squared for the second variable. This you will need for your standard deviation, sx and sy. And then, of course, for covariance, we would also want to figure out the product of the two deviations from the mean, right? So that's what we will have to calculate to figure out covariance and correlation. So let's go about doing that. How much is x bar? X bar is nothing but the mean of x, which is basically sum of all the xi divided by n. And for y bar, you will have to add all the y values divided by n, right? So we have a sum total of 5, 10, and 15 to be 30, and n is 3. You have 3 observations, and hence x bar turns out to be 10. And similarly, y bar turns out to be 90 over 3, which is nothing but 30. Make sense? Now, we would take each value of x and see how far is each value away from its mean. So mean is 10. And so we would like to see how far is each value away from its mean. And we do the same thing for y, whereby y has values 10, 30, and 50. And the mean is 30. How far is each of these y values away from its mean, right? So this will give you minus 5. That's 0. That's 5. That's minus 20. This is 0. And this is positive 20. Now notice, of course, the sum total is 0 in each case. Then you would want to square these deviations of x's and y's, And so minus 5's square is 25, 0 square is of course 0, and 5 square is again 25. For yi minus y bar square, it's minus 20 square, so that's 400, and then again 0 square, which is 0, and then 20 square, which is again 400. With me? And so what is the sum total of xi minus x bar? That's 50. Y minus y bar square, that's 800. And then we need the product of this column and that column, which is minus 5 minus 20, which is 100, then 0 and 0, that's 0, and then 5 times 20, which is again 100, right? And this total turns out to be 200. Now notice to figure out correlation, we first need to figure out the covariance, right? We have all the ingredients necessary to figure out the covariance. You need xi minus x bar multiplied by yi minus y bar. We have that. And then we need the standard deviation of x and standard deviation of y. And we already have the variance of x and variance of y ingredients. So let's figure out how much is the standard deviation of x, which is nothing but the under root of all the squared deviation average of them, right? And so this turns out to be sum of xi minus x bar square. We have already calculated to be 50, and then divided by 3 minus 1 and the under root to figure out the standard deviation, which will give you 25 under root, which is 5. We do the same calculation for y to figure out the standard deviation of y. That is the under root of squared y deviations, and then you are going to take the average across all the observations adjusted for degrees of freedom, right? And so we have a sum of yi minus y bar equal to 800, and then n minus 1 is 3 minus 1, and that is under root of 400. That turns out to be 20, right? So now we have calculated standard deviation of x, standard deviation of y. We have the covariance we have of the ingredients of covariance. So we'll have sxy, which is nothing but sum of all the xi minus x bar multiplied by yi minus y bar, sum it across all observations, and then you would want to divide by n minus 1. Sum of xi minus x bar times yi minus y bar, we already have calculated, that's 200, and then you have 3 minus 1 as the degrees of freedom, and that will give you 100, right? And so the correlation between any two variables is the covariance of the two variables divided by the product of individual standard deviation, right? So the covariance is 100 in this case. The standard deviation of x is 5, standard deviation of y is 20, so that's 100 over 100, which is 1. So basically that means that there is a perfect one-to-one correlation between x and y. And I think in some sense the simplified version was clearly indicative of that. If you look at the values of x, 5, 10, and 15, and so is the case with y values 10, 30, and 50. These are both increasing, and hence one can expect that there is a positive correlation between the two. And in this case, it turns out to be a perfectly positive correlation between the two variables.